Okay, let's get started. First of all, before the class, we have a quick announcement. So MP1 is going to be out today. So after the class, we're going to post it on the course website. So have fun. And also, we have another announcement. Okay, see it. So we have some students that haven't registered for Coursera platform. Coursera platform, and we want to make sure all of you register for that platform because we need that platform to submit the MP. So make sure you go to coursera.illinois.edu and register yourself with your NetID and an AD password so that we can actually add you and enroll you into the course. So before we start today's exercises, let's go over the snapshot algorithm. Is it on?
Okay. Hi guys. So I hope all of you have gone through the lecture video posted on the website. Before we start solving the problem, I'll just run through the Chandy-Lamport global snapshots algorithm just to put everybody on the same page. So obviously in a distributed system, having a entire picture of the system as a whole at one point in time is important. And Chandy-Lamport is an algorithm that gives you a global snapshot of the entire system. So I'll quickly explain how the algorithm works. So let's consider that the distributed system comprises of a set of processes. There's always one process that's the initiator of the algorithm, and that process is called the initiator. So it can start the algorithm anytime, and before it starts the algorithm, it firstly records its own state, and it also creates once it records its own state, it creates a special message called marker messages. So these marker messages are different from the application messages floating around in the system, and they're also and along the communication channel, they're ordered in a FIFO fashion. So they're sent after the application messages. And when I meant a FIFO channel, I meant that if an application message is sent first and if the marker message is sent next, the application message reaches first, and then the marker message reaches the other processes. And of course, this marker message does not interfere with the application message as such. Once the initiator sends out the other messages, let's call that process PI. And then once it sends out all the messages, to all the other remaining processes, PJ, it starts to record the state of all the incoming channels. So all the channels CJI, it turns on recording on all these channels. And now let's move on to all the other processes that are not the initiator process. So when a process PI receives a marker message, it does one of the following. Obviously, it receives a message on the channel CJI, like we discussed in the earlier slide. So once it receives the marker message on the incoming channel CJI, if it's the first marker message that it's ever seeing, then it begins to record its own state, and then it marks the incoming channel as empty. So the channel CJI state is marked as empty, so it's just a null set. And then it sends out marker messages to all the other processes except the process from which it received the marker message. So it sends out a marker message to all the other processes on the channel Cij. And then at the same time, just like the initiator, it begins to record the state of all the incoming channels CJI. Of course, except the channel from which it received, because that has already been marked as empty. And the second case is where it's likely that a process might have been seeing a marker message for the second time or a third time or whatever. In that case, what happens is that it marks the state of the incoming channel as all the messages received from the time it began to record its state up to that point. So, and then of course, it stops recording. All the messages that it received from the time it started recording its state. So if that process is called PI, so from SI, when it began to record its state up to the point when it receives the second marker messages. So all the messages in that timeline will be the state of this process, will be the state of that channel CJI, and let's think that there were two messages X comma Y. So it would mark these two messages as the state of the communication channel CJI. Might sound very confusing, but we'll solve a few problems to make it more clear. Okay. So we have distributed the exercises to all of you. Anybody who doesn't have the sheet with you, just raise your hand. Okay. Let's start with problem 1. Since we have just 4 problems today, we can give each problems more time. So probably you can take the next 10 minutes and solve the problem. And please solve the problem on your own. Don't discuss it with your neighbors. If you have any doubts or questions, just raise your hand and then one of us will answer your questions.
you please raise your hand if you didn't finish? Okay, so most of you finished? How do I put it on the screen? Which button? Something. Let me just. Okay, so let's go over the solution. So what you need here is for each process to save its state, and at the end to have a consistent state where we can roll back in case something happens. In our case, P2 is the initiator here, where it saves its state and then sends marker messages to the other two processes. And also, it starts recording on channels from processor 0 to processor 2 and from processor 1 to processor 2. The first message received is by P0 here. It's the first marker that it receives, so it can save its state. And both S2 and S1 include A being sent. It knows that this message came from P2, so it can close the channel C20. And then it's only waiting for a marker message from processor 1. So it's recording C10. And then sends two marker messages to the other two processes. Here, P1 receives its first marker message, so it records its own state. This marker message was received from P0. Yeah, you're right. S1. And this one was S0. So the state of processor 1 will be saved by processor 1. The message marker was received from processor 0, so we can close the channel from processor 0. And we don't have anything in the channel because no message was sent from processor 0 to processor 1 since processor 0 saved its state. And then we're recording the channel from processor 2, so 2, 1. And then we're sending marker messages for the other two processes. Processor 2 receives the marker message from processor 0. It's not the first marker message, so it doesn't need to save its state. It was already saved in the past, but it can close the channel from processor 0, so it will close C02. And again, we don't have any message between the two processes, so the channel is null. The next marker message received by P0 here. It's not the first one, so it doesn't need to save its state. The marker message comes from processor 1, so you can close the channel C10. And at this point, for processor 0, both channels were closed, so it's not waiting for any marker messages. So at this point, processor 0 knows that it's safe to roll back to its last save point. Processor 2 received its last marker message here, and it's coming from processor 1, sorry. So we're closing that channel. Again, as before, processor 2 ends, it's not waiting for any marker messages. And then at the end, processor 1 receives the last marker message from processor 2, and it closes its channel. And at this point, if they need to roll back, P0 can roll back to this point, P1 will roll back to this point, and P2 will roll back to this point. These are the points where they save their state. Yes? B1, 0, here, you're saying? Yeah, but B is sent from processor 2 to processor 0, right? Zero to. Okay, what's there? So no, let's look at the end. Let's see if this is correct. So A happens before S0 and before S1, right? So A is included in S0 and S1. Is that correct? Then B happens, it's between P2 and P0, and it's happening after S2 and after S0. So in case you need to roll back, B will be resent by P2 and will be re-received by P0. So you don't need to save it. Okay, is that clear? Yeah. So with this algorithm, you only need to save an event when you first receive your marker message. That's the only time when you need to save. Yes, and you saved it here, here, and here. Oh, when you're saving the channels. So you will see that with the second problem. I think it's easier to explain it on an example than just.
So for the channel messages, the trick is when each, for example, in this case, at this point, P2 receive a marker from P1. At this point, P2 close up its channel from 1 to 2, which is C12. So all you have to do is to look up the moment that P2 opens up this channel and P2 close up this channel, which is from this time point to this time point. So basically from this time point to this time point is the time that P2 opens up channel 1, 2. And during this time, you observe if there's any message from P1 to P2. If there's not, then this channel is empty. So let's say if there's an application message, during this time, like this, then this message will be recorded. Is it clear? Okay, if it is, then we can move on to the next question, and 2 questions after that. So we have 3 questions left, and you'll have 15 minutes.
Is everybody done with solving problem 2, 3 and 4? Is everybody done with solving problems 2 and 3 and 4? Is anybody solving one among problem 2, 3 or 4? Still? Okay, so we can discuss the solutions then. So let's start off with problem 2. In problem 2, P2 is the initiator. So it records its state S2. So when you say S2, it's the state of all its key registers.
Still true. Okay. So maybe you can hold it. You can hold it in one hand.
Okay, so P2 is the initiator here, and it begins to record its state once it sends out the marker messages to all the remaining processes. The state itself includes a state of its program counter, heap, etc. So you can just say S2, and then it also turns on recording on the channel, other incoming channels C02 and C10. And then the first marker messages, the first marker message that P0 gets is here, and then it records its state S0 at this point. And then can somebody tell me what else happens here at this point? So which channel is marked as empty here? That's right. So C20 is marked as empty here, and then it turns on recording on which channel at this point? That's right. So it begins to record on channel C10 at this point in time, and then the next thing it does is sends out marker messages to all the other processes. And let's move on to the next process, P1. P1 receives its first marker message at this point, and then it records its state S1 here, and then which channel is marked as null here? Okay, that's correct. C01. And which is the channel on which it begins to record its state? That's correct. So it begins to record its state on C21, and then the next thing it does is sends out marker messages to the other two processes. And then let's move on to the second marker message received by process P2. That's here. So what happens when a process sees a second marker message? Can one of you raise your hand and tell out the answer loud? Okay. On which channel does it record its state when it gets a second marker message? Where is the marker message coming from? P0, right? So it records a state of channel C02 as all the messages that it got from the time it began to record its state here to now. And what are those messages? Yeah, so it's a null set, so it'll be just null. And I lost myself here. And then this is the second marker message that P0 is seeing, and it's getting that marker message from P1 here. So that it's supposed to mark the state of channel C10. So, and that state is all the messages it got from the time it began to record its state here up to here. Do you see any messages coming from P1 in this time interval? No. So yeah, so it's again null. And then let's move on to the second marker message received by process P1. That's here, and it's getting that marker message from S. Yeah, it's getting from P2. So the state of the channel it's supposed to record is C21, and that state is all the messages received from process P2 from in this time interval. And are there any messages coming from P2 in that time interval? Okay, I'm not able to see that. It's like fully messed up. So is it C? We can verify it later. And then this is the next marker message that process P2 receives. And so which channel is it supposed to supposed to record the state on? Which is that channel? The message is coming from P1, so it has to be C12, right? So C12, the state of the channel C12 is all the messages it got from in this interval. So this slide is a little messed up. Let's move on to the slide that has a solution. So yeah, so we were right. So it was C here and D here. Okay. Is everybody clear with the first two problems? In interest of time, I just run through the solutions itself. A lot of people have other questions. So in this question, you're asked to mark all the Lamport timestamps for application messages only. So you should not include marker messages as a part of the Lamport timestamps evaluation. So we already did this on Tuesday's exercise, so I'm just going to do a few. Let's begin with process P1. So every process begins at a state 0, and then for every send event you increment the logical timestamp by 1. So the send event here increments from 0 to 1, and then the 1 is sent along with the message, and it's received at process P2. The process P2 does a max of its previous local timestamp 0 and the timestamp on the message 1. So the max of that is 1, and it adds 1 to the max, so it's 2. And then again, similarly for P2, it's 1 here, and then 1 is sent along with the message. And then the next message is going from process P2. So for every send, you just increment the previous timestamp by 1, so this becomes 2. And even the timestamp 2 is sent along with the message. And then process P0 receives the message here at this point. So it does a max of previous timestamp 1 and the timestamp on the message 2 plus 1. So that is 3, and so on and so forth. So all of you just quickly verify your answers. Did anybody get any different answers on this question? I'll just leave the slide for the next 1 minute. You can verify your answers. Additionally, we've also marked the state of the Chendi-Lamport state, but this question doesn't require you to do that. The fourth question is also similar to the third question. So again, let's solve a few messages and verify the rest of the messages from the next slide. So process P2 sends a message C. So this is a vector timestamp. So in vector timestamp, every process maintains a vector, which includes the state of every other process in the system. So there are 3 processes. It will be a vector. It will be a tuple of length 3. So it will be like 0, 0, 0. So process P2 sends out the first message, which means since it's a send event, it increments the ith element in the vector by 1. So here it increments the second vector. I'm using 0 indexed vector. So second element is the third one here. So it will be 0, 0, 1. And then the 0, 0, 1 is sent along with the message. And then let's move on to process P0 here, where it sends a message A. So for a send, the 0th element in the vector is incremented by 1. So 1, 0, 0 is sent along with the message. And that message is received at this point here in P1. So when a message is received, 2 things happen. Firstly, the ith element in the vector is incremented by 1 because it's a receive event. So the middle element becomes 1. And then the remaining elements of the vector, you just do a max. So you do a max of 1 and 0, so that's 1. And you do a max of 0 and 0, which is still 0. So you continue the timestamp for all the rest of the events. So this is similar to what we solved in the exercise on Tuesday. So you can, all of you can verify your answers on the slide. So anybody has questions with respect to this exercise? Okay, if none of you have questions, we are done with class. And some of you had questions about the Chendi-Lamport slides, so you can come and ask us here. One second, she has a question. No, we've just additionally just marked the, we've used Chendi-Lamport to mark the global snapshot. Yeah, so it's just a process state. Instead of marking it as S0, maybe we marked it as SA.